All right, everyone. So welcome to the second part of the homework for the heat transfer part of this class. Last video, we derived the heat diffusion equations for our spherical and our Cartesian coordinates. And so this video, what we're going to be working with is something called finite differencing. And basically what we're going to do is we're going to model the evolution of temperature in a bar, any bar, only worried about the x component. And we're going to say what's the heat temperature going to evolve like over time when we raise the temperature at the sides, at the ends of the bar, to different higher temperatures. And so that's what we're going to be working with. And that's great because we have the heat diffusion equation right here that's going to allow us to model that. And we're going to do some coding for that later on. But first, let's derive the equation we're going to be doing. And to that, we're going to really be doing three things. One, like I said, we're only going to worry about the x component for this because we're going to keep it pretty simple. And the second thing we're going to do is we're going to assume that there's no heat generation and that we have constant properties. So with all those assumptions, let's see how much we can simplify our heat diffusion equation. All right, and once again, this is just what we found in the last video. It's the heat diffusion equation for Cartesian coordinates. So only worrying about the x direction, let's just not worry about any of these terms here. And I also said we're going to assume that there's no heat generation term, so that also we're not going to worry about. Well, that leaves us with our partial with respect to x of k, partial of our temperature with x, and that's going to still be equaling our energy storage term here, which we defined previously. All right. Now, the last thing we could do is we're assuming constant properties, so we can actually pull this k out because it won't be, this partial won't depend on it because we're going to assume constant properties. All right, so we can pull this k out here. And when we do that, we see, well, we're just taking a derivative with respect to x of our temperature with respect to x. And we can write it that way, or we can just write it as a second order partial differential equation. Partial differential equation. Respect to x squared. All right, so we can write it that way too because we're just taking the derivative of the derivative, and that's what that is. And we'll just keep this over here, this rho Cp, partial temperature with time, our energy storage term. All right, so this is close to the equation that we're going to be doing for our computations, but for the sake of making it simpler, what we're going to do is go ahead and divide our rho Cp on this side. So we have K all over rho Cp, our density, our thermal conductivity constant, over density times our specific heat capacity. And now that's going to be multiplied by our partial second order here. And it's going to be set equal now just to our change in temperature with time. And what we're going to do to make this simpler is just call this term here alpha. We're just going to call that term alpha, all right? And so once we do that, we can just write this right here, alpha, or that's a terrible alpha. Let's rewrite that. All right, our alpha. Man, I don't know if that was much better. I think it'll do. Our alpha second order here, partial differential equation, temperature with respect to x equals our change in temperature with x. And so you see right here, this is our equation that we're going to be working with for this problem. And it's quite a bit simpler, given that we had a lot of nice assumptions. We can make this quite a lot shorter than this big general equation up here. So we're going to be working with this, and what we want to do is we want to solve this problem numerically. So to do that, we're going to need to do some defining some terms here so that we will actually be able to do that when we go to code. So that's what I'm going to do now. I'm going to clear up some space, and then we'll get right to that. All right, so what I've gone ahead and done here is kind of drawn out a little model that we're going to use to describe the situation that we're trying to model. So, like I said, we're going to be worrying about a bar of some sort, of some temperature starting out. And we're worrying about what's going to happen when that temperature has different, when the temperature at the ends is actually raised to something else. And we're going to worry about what the temperature is going to look like when it goes into this bar, basically. So that's why we derive the equation for our x direction only, because that's all we're going to be worried about. So let's think about what this might look like. So here I have a bar, and let's just say it's 1 meter long. And the way we're going to solve this is by cutting up a bunch of little slices of this bar. You know, a ton of little slices so that we can describe what's going, as the heat's going into it, what's going on. So if this bar is 1 meter and I say have 10 slices from 0 to 9, that'll be 10. Well, then each one of these is going to be, say, 0.1 meters. Each one of these slices is going to be 0.1 meters across because we've cut it up 10 times. Now, not only do we have to worry about the temperature as it goes into the bar positionally, but also there'll be some time component too. So the temperature is changing with position and with time. So, you know, we could have some time component too, where maybe this is 0.1 seconds. We're looking at every 0.1 seconds, you know, what the temperature in this bar is at 0.1 meters at 0.1 seconds. So really what we want to derive, or what we want to create now, is some sort of a term for temperature that will describe what the temperature in this bar is at some position. We'll call that J. At some position along this bar, one of these slices, at some time as well. So some time, all right? So we'll call that T sub J to the end. All right, and what we're worried, what this is describing is actually just, like I said, the temperature at one of these positions at some time as well. So to remind us here, our x will equal some j. Our x will equal some j times the increments of x. All right. Well, in this case, it would be 0.1 meters. If my j was 4, then I would take 4 times 0.1 meters, and that would be how far I would go into the bar positionally to describe where it's at. And for time, it's going to be pretty much the same. The time, well, that's just going to be equal to our n times some delta t. So if we're doing 0.1 seconds at a time, looking at 0.1 second increments, then 4n would be 4 times 0.1. All right, my t and my j and my n don't have to be the same. I could describe the temperature 5 seconds ahead at, you know, the first position. So this way, we now have a term that can kind of describe what is the temperature at a position and a time. And we're going to use that and expand that a little bit more so that we can solve this numerically. So next thing I'm going to do is try to use this nomenclature here and plug it into this general equation that we found for our problem. And we'll see what we get here. So I'm going to do that now. So now that we have a term here that can describe what's going on in our bar in terms of temperature for position and time, let's now think about how we can use that for our equation that we just found. So what we want to look at here is what we see is this is we're taking a partial here of time, our temperature with time. So what it's describing is how our temperature is changing with time. We can think of derivatives kind of like slopes. So we want to look at the slope of something. We look at the position at some point later on, some point here minus some point here over the distance that it transversed over. All right, and so we do the same thing with this term here. The partial of temperature with respect to time, how can we put this Tj to the end there? Well, let's see here. So my position is going to be the same. My Tj is going to be the same position for this. But it's going to be at some time n plus 1 minus a temperature at some same position at a time n. All right, that's the change in temperature I have. And we're doing that with respect to time. So we're doing it over some delta t over time. All right. So you see, we just used this term we found here and expressed it now with our equation that we found. Let's do it for the other one. So that's going to be equal. That'll be equal to some alpha. All right. And let's write this out the long way here first. Our partial with respect to x of our change in temperature with x. All right. well, how can we describe our change in t with x? Well, it's just going to be exactly like our change in t with time, only this time it's going to be with our position, so it'll be with our j. All right, so that's another way we can write that is t at some j plus 1 position at the same time minus t at some original position j, at the same time over some x that we're varying it over, some delta x. All right, so we've just described it for almost every term now. How do we get rid of this last partial here? Well, if we look at that, this term is just going to be some term here minus another term that we'll describe as the difference between this temperature with one x and a temperature with another x, and it's still over x. So to make that a little bit clearer what I just said there, let's think about another way we could express this term. All right, we could describe this term also at some tj, some position, all right, at the same time minus tj to the this time instead of dealing with one to the right, we'll deal with one j to the left. All right, so you see that this is tj minus 1. So I have a tj minus my tj minus 1 over some x. Likewise, here I had one position to the right minus the position to the left of that one. This one I have the position to the right minus the position to the left of this one, all right? So it's the same thing. It's just another way we can express this term, and it's describing the same thing. And this is great because, well, the partial of this term with respect to x will just end up being this minus this over delta x. And you see why? Because now we're taking this whole thing as a term minus this whole thing as a term over the x we're varying it over, which is exactly what we did here. It's just a little bit bigger now. All right, so let's go ahead and do that. So that'll be, I'll go ahead and rewrite everything down here. So our tj to the n plus 1. Sorry, temperature at some position j at a previous time over time equals alpha. All right, times this term minus this term over delta x minus tj plus 1 minus tj over delta x. Oops, that minus should not be there yet. So this term minus this term minus this term over delta x minus this term here, which is tj n minus tj minus 1 over delta x. And we're setting this whole thing, that's our numerator, and we're varying that whole thing over x. All right, we're varying that whole thing over x. And so let's go ahead and make this simpler one more time here, and then we will be in a good shape. This is my tj n plus 1 minus my tj to the n over some time equals, you know what, so what I see here is I see delta x, and we can think of that, remember this is delta x over 1, and we multiply it by 1 over delta x. So let's just go ahead and pull out delta x squared so that we don't have to keep writing all these fractions. We'll pull out delta x squared, and we'll have alpha over delta x squared. Alpha over delta x squared there. And we pull that out, and then we're just going to be left with, in parentheses, our tj plus 1 minus our tj minus our tj to the, and sorry, these are all supposed to be the n's. I didn't put the n's there when I was writing it, so these are all to some n, and it's the same n because this is just with x, so we don't care about the time. It's going to be the same time. So I'll write those here as well. N to the n, same n. Yep, minus tj to the n, minus tj to the n. Finally, minus tj to minus 1. Nice one. Some position to the left, also to the end. And we took out all the x squared, so that is going to be that. All right, so we pulled everything out. One last thing I see here is I see 2 TJs to the n. So let's just subtract those and combine those together. So this is going to be TJ to the n plus 1 minus TJ to the n. And let's go ahead and multiply that delta t over to this side, and we'll be equal to delta t times that alpha over delta x squared over delta x squared. And combining terms here, we just be left with tj plus 1 to the n minus 2 tj minus 2 tj to the n minus, same thing, tj minus 1 to the n. All right, here, almost done. So what I see here is, well, we have if we isolate this tj to the n plus 1, we'll have a term that will be set equal to something that is describing the temperature change as time goes on, because this is the temperature at some position at a later time. So if we just put that temperature j to the n over there, we'll be in good shape and can start doing some cool stuff. So let's go ahead and do that. Make sure, yep, tj plus 1 equals delta t alpha over delta x squared. All right, our time alpha we defined for our position squared, and it's going to be tj plus 1 n minus 2 tj to the n minus tj minus 1 n, and then we're moving this over to that side, so that's going to just be equal to plus that term now, plus tj plus some tj, some temperature at position j at a time of n. All right, and so this is the equation we're going to start using. This is the equation we're going to use for solving the problem numerically, and I'm going to show you how we do that next. All right, so actually before I go to the coding element, I wanted to draw out one more time the situation that we're looking at here. So we're going to have some bar of material. And for this problem, we're going to assume that this bar starts at a uniform temperature of 300 Kelvin. And what we're going to do is raise one side of this bar, raise the temperature at that side up to 400 Kelvin. And we're going to do something on the other side. We're going to raise the temperature at this side of the bar up to 350 Kelvin. And what we want to know is somewhat precisely how that heat goes into this medium and what that's going to look like. And we're just going to use that equation that we just found to solve for this numerically. And we're going to do that with some coding here. But this is the situation that we're looking at. 300 Kelvin, raise the sides of the bar up to a higher heat, and how will the temperature go into the bar? So let's go over to the coding element now. All right, so the first thing we're going to do is import our numpy. So import numpy as np, and we want to make some subplots. So from plotly dot plotly dot subplots, I think. Subplots. We're going to import make subplots. Oops. Make subplots. And because we know that Carlos does not like white graphs, we're going to try to do this in dark mode. So import plotly.io as po dot that'd be templates dot default, and we're going to set this as hopefully plotly dark here, plotly underscore dark. All right, so this is, we're going to be working in numpy, and we're making subplots, so we're importing that subplot from plotly, and we made it dark mode so that hopefully Carlos will like it a little bit better. So that's what we're going to be doing. Now let's get to the actual specifics of the equation we got from our problem, and let's start coding that into our next cell. All right, we're going to do that now. So next, let's start getting to the specifics of our problem here. So I'm going to click Shift Enter. Should work. Yes. Yep. All right. So we're good. So let's define first the number of time steps we're going to be walking through. So that'll be, I don't know, we can set that as anything. We'll do 20,000 just to be safe. We'll do 20,000 time steps. And let's define how many slices that we're going to do as we slice up this bar into a bunch of little tiny pieces. Let's just start with 100. We'll start with 100. And now next thing I'm going to do is define an R. And this R is going to represent that delta t alpha over delta x squared that we had in our overall equation. And we know that's just going to be equal to some constant. We're just going to define it as R and say it's 0.1 for the sake of computation. So we'll just define that like that. All right, so now we're going to go on and put our bar in terms of an array, actually a matrix, and then we're going to try to make that matrix just a row of numbers as that heat is going in. So let's do that now. So to do that, we're going to do our temperature is going to be some matrix, np.full, and we want our matrix to be in X because that's the number of slices, and we want all of them to be, as we've said in the previously on the whiteboard, we want them all to be starting at 300 Kelvin. All right, 300 Kelvin. Shift Enter. Yep. And so now let's think about our boundary conditions, the things that are happening at the ends of our bar here. So we said we're raising one side up to 400 and we're raising the other side up to 350. So let's define from our matrix here our zeroth term, which in Python is the first term. Here, I'll show you that right here. You know what, let me show you down here. So T, Shift Enter. Yeah, so we have an array here, and so this is our zeroth term, and this will be our -1 term, actually. When we define it in Python in the indexing, we'll just define this as our -1 instead of trying to count, which would be like 299 when we were if we were to index it that way. But for the sake of versatility, let's just call this T0 and the other one and our other one as T-1 to define our beginnings and ends of our bar here. So T0, T-1. And we said that the left, we're going to set that equal to 350 Kelvin, and the right, we're going to set that equal to 400 Kelvin. All right. So, oops, Shift Enter. All right, so hopefully when I do T now, it'll be the same thing, an array, all of 300, but the ends will be 350 and 400. And yep, that looks like what we got here. Perfect. So now we have our boundary conditions set up for our bar. Let's make this now not an array, but just rather just a row of numbers. So this, we're going to do a range, x equals np dot a range. Is that right? Yeah, a range. And we're going to do so a range, and we're going to do an x, right? Shift Enter. So now let's look at our t. So before we get into putting that equation we found on the whiteboard into this, let's think about what we're trying to do. We want to make some plots of our temperature profile over time so that we can see how it evolves. So let's go ahead and put some plots in here. So let's do, that would be make subplots. I want just one row. Rows equals 1. Columns equals 1. And it's just going to equal 1. Just a 1 by 1. And we want to, let's see, fig dot add something like scatter, where x is going to be equal our x, but our y is going to equal our t that we just defined. And of course, we still have to say what t will be, but it's going to be that array. We'll do it as a line graph. Mode equals line, and come up with a name for it. Our name could be, I don't know, T profile, something like that. All right, so this should be this should allow us to make a plot of it when we're done. So let's go ahead and put our T into it now. All right, so what we want to do now is we're going to incrementally upgrade or update our T that we will put in a minute. So to do that, we want to put it in a for loop. So for I in range from 1 to our for our time step nt plus 1. So to go through all our time steps here, we want to have some t, which we will define, but we just wrote on the whiteboard. So we'll put that t in there in a minute. When we do that, we want, hold on here. When we do that, we want to add in that. So basically, the problem is we have 20,000 time steps here, and we don't necessarily want to look at all 20,000 of these lines. So we're going to tell this that we want, if we want every time step to be updated, or if we want, say, every 100, maybe every 1,000. If we got 20,000, let's do every, if I is for every 1,000 here. Trying to find it. Where's the part? There it is. For every 1,000. So for every 1,000 time steps, we're going to put what that temperature profile looks like onto our graph at the 1,000th, at the 2,000th, 3, and so on and so forth. That way, it's not too cluttered, and we can see a little bit more what's going on. And when that happens, we want to add that into our plot. So that's fig.add scatter, and the same thing as above. X equal to x, y equal to t. Our mode equal to lines and name, and this is just so that we can add it in for every 1,000 there. That's all that's saying there, is that every 1,000 we're going to add that into this graph here, and then display it. And then at the end, that would be, at the end we want to show that figure so that we actually can see it. Fig.show. All right. So I think that we have all the bulwark around our equation done. Now that's all that I see that's left, is to, actually this should be fig equals, not just make, fig equals, make subplots. Now let's just put in our t here for our temperature profile, which is what we derived on the board. So let's do that now. All right, so now what we're going to do is we're actually going to put in that temperature profile equation we found on the whiteboard into our Python, and then we can finally solve for this and get a nice little subplot, hopefully. So I have written down here, because I don't have a whiteboard anymore, just so that you can be reminded of what we're doing. This is that temperature profile that we found here, and we have that on the whiteboard. So if you want, you can go back, and this is exactly what we left there. And only thing that's different, as I wrote down here, is that we are actually classifying that delta t alpha over delta x squared as r. Is going to be some constant, and we're saying that's r, and we're saying that that's just going to be 0.1 to make things a little simpler. So I have this in front of me so that I can code it in now, and this is all stuff that we found previously. So let's see here. Actually, I don't think that these are supposed to be. There we go. Yeah. Yeah, that looks right. Okay, so let's see. So we have some t, and so this is our tj to the n plus 1. So our j, remember, if we're looking at this as our bar, our j is just going to be everything from in between our boundaries there. All right, it's going to be in between our boundaries. So that means when we're setting what this t is equal to, or what I guess not equal to, but the dimensions of this t, we're going to do it 1 to -1. All right, and so that's because that 1 is this term right here. All right, that's that term. And this is the thing that is a little confusing about Python. That -1, while up here does mean this, it because the way indexing works, it's just going to be this term. So you can see we've defined this t as everything between the 350 and the 400. All right, yeah. So we have everything there. So that's what that's equal to. Equals, and now we have another tj. Just worrying about our position here. What are we going to do for that? The exact same thing. Even though it's to the end this time, it doesn't matter because we're just worrying about the position. So that's -1 there. Yep. Plus, now we have our r times tj plus 1 this time, or tj plus 1. All right, so that's going to be tj plus 1. Well, that means that we want everything from here this time, because it's plus 1. We were here, plus 1 is now here. So we want everything from that 300 all the way down. So what would that be? That would be t, and that would be, I guess, 1 and then 2, because we started 0, so that would be 2, and all the way to the end there. All the way to the end. And you know what? Actually, thinking about it, we need the t plus tj plus 1, which means that we are now actually including that 400 into this. So that is why we do go to the end for this one, because we're moving that whole thing over by 1. All right. So let's go on to our next part here. So I see minus 2 tj to the end. All right, that's easy because we know what that is already, which is just t and everything in between those two boundaries, big T that is, from 1 to -1 for that, -2. Almost there. We got one more minus. Now this time we're doing 1 to the left, so we got to include that 350. So, oops, that 350. So we're going to do 1 to the left, not starting at 400, but not starting at this 300 rather, but at this 300. So that's going to be -2. Or is that -2? Because this -1 is this term, so -2 would be everything from here to the 350. So -2. All right. -2. So let's see. Does this match our thing? So there's tj to the n, tj to the n, and then this is our other tj to the n. They all have the same parameters. Our r's there, yep. Our t to the j plus 1, that's good because we have starting now from 2 to the end, and our t to j minus 1 we have from the n to -2. So just using this equation we found from the whiteboard, that's what I used to code that, and you can see the logic behind it. And now we're going to see if it generates our temperature profile evolving when we put it in. So let's do that now. All right, so I'm going to run this and see. Hopefully we get what we. Hopefully we should get a plot that every 1,000 time iterations has the temperature at that time. So it doesn't like our syntax. Okay, so this range here, it looks like that needs to be. Oops, that range. There we go. That range needs to be, there's a space there. All right, let's try it now. Still doesn't like that. Okay, so this I should be I think so. This needs to be equal 0 equals 1,000. So I got confused on that part. 0, then every 1,000 iterations we add that. That might have been messing it up. Let's try that now and see if it works. Still doesn't like this. Let's see. Invalid syntax for I in range. For I in range from 1 to nt plus 1. Alright. Does there need to be another space here? Maybe? Let's try that. Nope. Alright, we're going to take a look at this here real quick, and then we'll be right back. Okay, so I think what happened is here is this needs a colon. We didn't put a colon there, and this needs a colon. Also, we still didn't do this right. This is supposed to be 0, and this is saying every 1,000. Every 1,000, we're going to put that. So we switched those two there. Now we put the 2 colons there. We switched those two. I think this time it'll work. Let's try it. Let's try it this time. It doesn't like that. Let's see why. Let's see here. First of all, I don't know what happened there. Y is supposed to be equal to t. Maybe that was it. I don't know. I'll try it. Nope. Alright, we'll look at this one more time here. We're almost there. Okay, so going back to our board here, I just noticed one glaring mistake, and that is that we are subtracting here, and we're subtracting here. So that's minus a negative, which means this is always supposed to be, has always supposed to be plus tj minus 1. Plus tj minus 1. That's going to matter big time when we go to put that t into our coding, or into our code that we have. So that's supposed to be plus tj minus 1. Now that this is actually the correct equation, let's go ahead and plug it in. All right. Okay, so now that we've fixed our equation on the board, let's fix it here. So as you see here, this is our minus term, minus our tj minus 1. This, we said, is supposed to be plus. That is supposed to be a plus. And so that was part of what's messing this up here. Another thing is too, let's go ahead and make these all integers here. All these integers, just in case. That way Python thinks, we need to make those all floating. Otherwise, Python thinks these are all integers. So put a decimal at the end, and that way they will all be float there. And all right, I think this will work here. Perfect. There we go. So yeah, this is exactly what we expected. The temperature is going into that bar. You see that where the 400 is, it's going and elevating that faster than where the 350 is, right? This side is got a higher slope there than this side. But eventually, it all comes to a straight line, which is exactly what we would expect. All right. So that was doing it with an R of 0.1. Before we end this video, the last thing we're going to do is look at what happens when R equals 0.55, actually. And we expect, well, given privileged knowledge, we know from class that probably is going to look pretty ugly. So let's see here. Yep, and there it is. So these are some huge numbers. 6 times 10 to the 234th power. Wow. All right, so clearly there's an instability with the equation we had. But for an R value of 0.1, let's look at that one more time. It worked quite great, actually. Quite nicely, yep. So that's a great plot in dark mode, if I might add. And yeah, I think that's all for this video. We went through finite differencing. We used our Cartesian coordinate heat diffusion equation and narrowed it down and simplified it for our problem. Then we took
our equation and came up with some nomenclature and some terms that would be helpful for us to solve it numerically. And then we solved it numerically using Python, which can do a couple thousand calculations in a few seconds there. And we explained everything here and got this beautiful little temperature distribution. So that's pretty cool. Next video, we're going to talk about why that 0.55 makes it look a little bit crazy for the R. But for now, I think that's all. Thank you.